This is problem 1 for homework 7.2 and 7.3. Determine if the vectors 3x squared plus x minus 1 and x squared minus 3x plus 2 are linearly independent in P5. If these two vectors are linearly independent, then the zero vector can only be expressed as a linear combination of these two vectors with zero coefficients. So we can solve for the scalars a and b. A times 3x squared plus x minus 1 plus b times x squared minus 3x plus 2 should be equal to the zero polynomial. All the terms with x squared on the left-hand side in this equation should be equal to those on the right-hand side. So we will have this equation. And for x term, we can write the similar one. And for the constant term, we will have this equation. Solve these equations in the matrix form. We will get this as our reduced echelon form. Then we will know a is equal to 0 and b is equal to 0, which is the unique solution. Thus, these two vectors are linearly independent. B. The S is the span of these two vectors. Determine if the given vector v, 7x squared minus 5x, is in the subspace of P2. If the given vector is in the subspace spanned by two vectors, then this vector can be expressed as at least one linear combination of these two vectors. So we can solve for the scalars a and b and write the similar equation like the problem before. A times 3x squared plus x minus 1 plus b times x squared minus 3x plus 2 should be equal to v, which is 7x squared minus 5x. For the x squared term, we can write this equation. For the x term, we have this one. And for the constant term, we have this. Solving this system of equations in the augmented matrix form, we will find there's no solution, which means the v vector is not inside S. Part A and B are dealing with the polynomial vector space. Part C and D focus on the matrix vector space. In Part C, S is the set of these three matrices. Determine if the set of vectors S in R2×2 is linearly independent. Still, the zero vector can only be expressed as a linear combination of these vectors with zero coefficients if they are linearly independent. In the overall equation, the numbers in each position in R2×2 contribute one equation. There are 4 positions in R2×2, so we are able to write down the equations for each position. For example, the first equation is for the number in row 1, column 1. Solving these equations in the augmented matrix form, we have this, which indicates A, B, and C are all equal to zeros. And it's a unique solution, so the vectors are linearly independent. D. Determine if the vector v, 2, 3, 3, negative 3 in R2×2 is in the S, which is a subspace of these three matrices. If the given R2×2 vector is in the subspace spanned by these three vectors, then these vectors can be expressed as the linear combination of them. For each position in R2×2, we have one equation. Solve the A, B, and C coefficient in the augmented matrix form. We get the solution A is equal to -1, B is equal to 1, C is equal to 1. Thus, the V vector is in the subspace S.